finding Riemann sums here, all right? And 3.1 is titled Measuring Distance, okay? How do you measure distance? And we're going to look at measuring distance in the context where we're talking about how fast is a certain object moving at a certain time, okay? So the question is, how do we measure distance traveled from tables and graphs, all right? Guys, how many of you have the little Apple Watch thingy that you look at your number of steps you've taken in a day? Anybody have that?
Yeah.
I don't even know if I know how to operate mine. So, let's see. It's the little one with the rings, right?
Yeah.
So for me it says I've gone 2,286 steps so far this morning. Beat me.
16,500.
You probably went and ran already, didn't you? Show off. I do have good news, Ellie. I think I'm going to be able to start running again here
Come
sometime.
summertime, you're going to be.
Yeah. I'm only going 1.11 miles.
You're going to be doing marathons.
Oh gosh, let's not go that fast, all right? I don't know if the heart can take it now. The leg might be able to, but this. Okay. So, we're going to kind of talk about how do we measure distance right here traveled. And we're going to look at it relative to what we call graphs and tables. And to understand the question that we're looking at, how do we find distances traveled given velocities at certain points, we need to understand what's called left and right hand sums, okay? We're going to use tables to approximate a distance traveled, and we're going to also use graphs to approximate a distance traveled. And in order to do this, kids, kind of what we're looking at is the following, okay? We're going to be dealing with Riemann sums. Kids, we're going to be concerned with an area under a curve. So if you could kind of look at this curve right up here with blue, kind of watch where I go with this right here. Where are my tools? There we go. So what we're kind of looking at, guys, is this. We're kind of looking at, if you could kind of imagine from this graph right here, if this is my line right here, and I could shade in this whole area right here in red that I've outlined, I would say that distance is going to be what's called an area displacement under a curve. Now, guys, take a look at these bars that are up in here. These bars are rectangular in shape, aren't they?
Yeah.
And is it easy to find the area of a rectangle?
Mm-hmm.
Yeah, you would do length times width right here. But guys, when I divide it up into certain intervals right here, does this bar give me the whole area I outlined in red?
No.
No. So what we're going to talk about is how much error, or is this an overestimate or an underestimate in terms of the area under a curve. So the thing I want you to understand is this. We're going to be talking about Riemann sums. Riemann sums are going to be what's known as a left hand and I always abbreviate, a right hand sum. All right? We're going to be taking the area of these rectangles and adding them up. So a Riemann sum, like I said, it's a certain kind of approximation of an integral by a finite sum. I like to call it an area under a what? Bounded curve. So like if this was my start right here, and this is my finish, that part I outlined in red, that definitely has a certain area. But that part outlined in red has, gosh, is that a normal shape, guys? Kind of hard to find the area underneath that curve. So what we do is we start putting rectangles under there to approximate the area under there, okay? Guys, this first blue bar right here, this first blue bar, would the blue bar be an overestimate or an underestimate within this interval? There's more area in the blue than there is under the red for this interval. But what about this little blue bar right here? Okay, now, we're going to talk a lot about what happens with this right here. Notice the interval length in blue compared to the interval length in red. What happens to the interval of the bars here in red compared to the blue ones? They're smaller. So is there, let me ask this question. Is there more white area in the red curve here in this first part or more white area in this blue curve part? So which of these two graphs do you think is more accurate for an estimate for the part that I just bounded? The red. What happens if I make my intervals even smaller? More accurate, or even smaller yet. Doesn't this look like a pretty good approximation for the whole area right here? So if I could add the area of all these yellow bars up, wouldn't that give me a pretty good approximation of that bounded area right there under the curve? Okay, so here's what you're gonna hear me say. We're gonna talk a lot about left-hand sum and right-hand sums to approximate areas under a curve. And the thing that you're gonna find out that as we approximate areas under a curve, the smaller you make an interval for a rectangle, the more accurate your area approximation is gonna be.
So
Okay?
it's kind of like relief cuts when you're working with a bandsaw, like you're, I don't know, that's what it reminds me of.
Yeah, you could say that.
I don't know, that might be stupid.
Kind of like a cross-sectional type thing, in a way. Yes.
Okay. So, I guess the way I look at it is this.
If I can make these intervals really small, so close to 0, like the width of a piece of paper, and keep putting rectangles in, up to the graph right there, one next to another, wouldn't that give you a pretty good approximation? Okay.
All right, let's just talk about this right here. What's a left-hand sum first? So I think you have this idea that the area under a curve is going to be the sum of a bunch of rectangles.
Okay. Left-hand sum is a Riemann sum using a left-hand value for area calculations. So I'm going to use this bar right here. Here's f of x right here. Your function f of x, it lies right there for you guys. Okay? Now, if f of x lies right there, kids, take a look at your bars. Specifically, maybe this bar right here. If I look at this bar right here, kids. Okay. I'm going to look at that last interval right here. Within that bar, kids, does the left-hand part of the bar touch the graph, or does the right-hand part of the bar touch the graph? Okay, that's why this is called left-hand sums. So left-hand sums are going to be when you hit a point on the graph and say, okay, at this interval, for this particular interval, which I'm going to call delta x down here, it's a change in x. For this particular interval with interval length delta x, if I draw a rectangle under the curve to hit this, does the left-hand side of the rectangle or the right-hand side of the rectangle hit the graph? Okay, it's the left-hand one. It's the left-handed side, so it's left. So guys, if I found the areas of all of these rectangles right here to approximate from, say, this point, the area under the curve, from this point to this point, we would add all the areas of these rectangles up. That would give you what's known as a left-hand sum. Okay? Would this area approximation based on this graph be an overestimate or an underestimate for the total area? Okay, because is this area getting accounted for right here? Okay, so we've got some blank spaces in here. So do you understand why this is a left-hand sum?
Yeah.
What do you think a right-hand sum would be then?
The right side of a bar touches the graph.
So let's go to the next page and see if that's true.
So in my right-hand sum right here, guys, take a look at this. We'll look at this interval right down here.
I'll look at the last one again. So this interval has length from here to here, delta x. It's some distance. Delta x just means it's some distance. It might be 2 feet. It might be 1 mile. It might be a millimeter. Okay? I have no idea what it is. But what I do know is this. For this particular interval, I can get an area approximation. Now this bar right here, my friends, this bar went all the way up here, didn't it, kids? Now, I know it passes through here, but that's the right-hand point. So, guys, take a look at this very first one. Which point did they use first, the right-hand point or the left-hand point to draw their rectangle? The right-hand point. So the points they're using now are going to be the right-hand point. Guys, I think I need to calibrate this. Give me a second. I have to move some things around this morning. So you guys hear about that winter storm that missed us to the south by not too much?
Really?
Yeah, do you know how much snow it's dumping in Missouri or just south of Iowa?
How much?
Like 18 to 24 inches, they're thinking. That was on track to hit us like 5 or 6 days ago, and then it shifted south.
No.
So you guys almost had the rest of the week off. Close, but you know what? Missouri can have it. That's what I say. All right. Okay. So right here, guys, well put right here. A Riemann sum for right-hand sum is going to be a Riemann sum. And guys, it's called a Riemann sum because that's the guy who came up with this idea. So this name right here, it's just the name of the guy that came up with the idea. A Riemann sum using right-hand values for area calculations. So do you understand why this is a right-hand bar right here?
Yep.
Okay. I'm going to draw the left-hand bar in here. Isn't that where the left-hand bar would be?
Yep.
Okay. Quick question. Right-hand sum for that graph, overestimate or underestimate? Left-hand sum for that graph, overestimate or underestimate? Okay, and I think you get this right here. So guys, right here, we're going to talk a lot about overestimates and underestimates because, again, left and right-hand sums or Riemann sums are going to be some kind of area approximation, okay? You're either going to be over the actual value or under the actual value, but pretty close to it, okay? An underestimate, my friends, is an approximation from Riemann sums that are more than the total area under the curve, okay? I think I've got this, no, I've got this mixed up, don't I? This should say less than right here. I need to go in and change that today. This should say less than, and then this should say what? More than. Okay, do I have the right graph? I've got the right graph still, right? Okay, so take a look at this right here. All of these orange bars. By the way, is this a left-hand sum or right-hand sum? It's a left-hand sum. All the left points are touching the graph, okay? These areas in orange represent an approximation from, I'll call this point, say, maybe x1, and call this point x2 down here. So from x1 to x2, there's a total area under there. When I break it down into the total sum of the intervals and add the area of those rectangles up, this part right here gets left over. This is unaccounted for, isn't it, for area in blue? So this, my friends, would say this orange area is less than the orange and the blue areas put together, which would be the total. So this would be an underestimate right here. Okay? Then take a look at the next one. Why is my next one an overestimate? Yeah, the bars are going up and over the curve bounded by the x-axis from, say, x1 to x2 here. Okay? So, by the way, is this a left or right-hand sum for that one? That would be a right-hand sum. Okay, very good. Okay. So let's talk about this a little bit. I'll do the best I can with my graph. Let's talk example 1. Okay. I need to ask a question. Where are my science people at? A lot of times in science you talk about rates or speeds, how fast something is going. We'll let this start. Okay. Distance divided by time, what's that equal to? Typically you call it what? Like 55 miles per hour, right? Okay. So a distance d divided by a time t would give you what here, kids? Velocity. I have a question here. Title of the notes here said, how do we measure distance traveled, right? My friends, how would you get distance all alone up there if I had to have a formula for distance?
Multiply it by t.
You'd have to say what again?
Velocity times time equals distance.
Okay.
T equals RT.
Distance equals velocity times time, or some of you guys have probably heard it as distance is equal to rate times time, haven't you? Okay, so how do you want to do that? You want to call it R equals d over t, or do you want to call it v is equal to d over t?
It doesn't matter.
Okay, I'm going to be honest with you. In calc a lot, we talk about the word velocity more than we do rate. But understand that if you hear velocity relative to a speed, they mean the same thing. So let's talk about this. Knowing that distance is equal to a velocity times the time, let's talk about what we have in this graph right here. Whoops. So, I need to go to the next page. Okay, suppose that the following table represents the what, kids? Velocities in what? At a certain time in what?
of the car. It says use graphical measures to find the distance traveled over that time span. Okay? So kids, I've got a graph over here on the next page. I'm going to make a note right here. Two things. You said that distance was equal to what again, kids?
VT.
Velocity times time. My time up here is measured in seconds, right? All agree with that? And then this is going to be measured in meters per second, right? So at time 0, when we start timing this, how fast am I moving? 80 meters per second. Then at time 2, what's happening? How fast are you moving? 85 meters per second. So am I speeding up or slowing down?
Speeding.
You're speeding up. What's my velocity at 4 seconds? Okay, and what's my velocity at 6 seconds? So here's a question for you. I'm going to grab my board here to make a better graph. My question is, how far have you gone? And all of a sudden you're like, I have no idea. Okay? So here's what this is going to look like. Guys, I want you to stay on, well actually I'm okay with this. Maybe I can do it this way. You're going to flip over to page 3 of your notes. Okay, we're going to make a little graphical representation of this. So let's do this right here.
Wait, is this graph on here for the?
The graph on page 3 is for example 1. Yep, so I want you to go to the next page here. Okay, and I'm there at the top here, my friends. Okay. So the first graph we have right here, I'm going to make a note right here. This graph is for example 1. I'm going to need your help, kids. Okay? I'm going to go ahead and call this time down here. All right, so I'm going to go ahead and call this time 2 right here. So 2 boxes in, we'll call it 2. And I think it went all the way up to what, kids? 6, is that right?
Yeah.
Okay, so I'm going to label the x-axis on this for example 1. This is going to be my time down here. Measured how?
Second.
Okay. Now, I need some help here. What was the lowest speed?
80.
So I'm just going to pretend there's like a break in the graph here. Oh, no, what's going on? Yeah, man. Hang on a second, friends. Oh, we got it. There we go. Okay, I'm going to pretend there's a break in the graph right down here. Is that okay? Okay, so the first velocity was how much? 80? And it goes up to what?
110.
So I'm going to go by 2 boxes here. Okay, and these velocities are going to be measured in, what was it? Okay, so we'll put velocity here. Measured in. Okay. Kids, time, what was the first time that we started measuring? Okay, 2 seconds, but we got to start at time what really though, according to the table?
0.
Okay, at time 0, how fast were we going? 80 meters per second? So I'm going to plot that point right here. Okay, and then at time 2, where were we at?
85.
So that'd be right about here, wouldn't it? Time 4? Was it 95?
Yeah.
So it's time 4 will be 95 here, and time 6 is about, what was it, 110? I'm gonna go up here and draw my curve as best I can. So you guys see kind of what's happening here? At time 0, we were 80 meters per second. So we're speeding up. So at each time increment there, our speed is speeding up here. So I'm going to get a curve drawn in there as best I can. Let's see how this goes. Kind of close, aren't I? Hey. All right, let's talk about this, kids. Back to the previous page and ask me what it says for how do you estimate how far you have done what?
Before you travel.
Okay, here's what we start looking at doing, kids, and I'll show you why here in a second. But let's look at the left-hand sum here first, okay? How long should each time interval be? In other words, how often or after how many seconds were we timing all the time?
2.
So what we're gonna do here, kids, is this. We're gonna start putting some rectangles in here. And I'm gonna start doing rectangles for left-hand sum. So I'm gonna start at 0. I'm gonna go all the way up to my graph. I'm gonna draw a rectangle right there. Okay, that's the first one. Then, what am I gonna do after that?
Draw another one.
Make another one between what and what?
2.
Okay, so let's do that. Between 2 and 4. So I'm gonna start right here, say, all right, go all the way up until which one hits?
Left.
And then go right with it, right? Does that look about right to you guys? Oh, come on, boogie board work. Okay. How many total boxes am I gonna end up making here for left-hand sum? Three of them. We're going from time what to what?
0 to 6.
That's working.
So you wouldn't need one touching each point. You just need one touching.
Gotta make sure you cover your whole interval here. I gotta do something here quickly. Hang on a second, kids. Isn't technology great? What's the old saying? Technology is great when
It works.
it works. Trying again. Things made by the Ford company around here. Okay, I might have it here. Okay. Guys, a left-hand sum, check this out. Haven't we covered the whole 6-second interval from 0 to end at 6? Okay, think about this, kids. Down here it says we use left and right-hand sums to find distance traveled. Why do I do that? Well, here's the deal. Guys, take a look at this down here. What's this length right down here from 0 to 2? So that's like a change of 2 seconds, isn't it? And then, what's the change from 0 down here up to 80? Okay, but that would be in meters per second, right? I'm gonna kind of jump down here. Why do we use left and right hand sums? Well, you'd be like taking 2 seconds, right? Times What's the height of this rectangle right here again? 80 meters per what though? My friends, what do the second units do to each other when we multiply a time times a velocity? What do the second units really do to each other? And so what I'm left with is 2 times 80 meters, which is how much? So the area of this little bar right here tells us you've gone about 160 meters, okay? Because the second units would cancel when you take your length unit times your height unit. And so guys, in that first 2-second interval, I have a question. Is that 160 gonna be an overestimate or an underestimate for distance traveled? Because we didn't account for this little part right here, this little triangular shaped part, right? Okay, next question here. How much time is elapsed from 2 to 4? We're gonna take 2 times, what's the height right here? Okay, what's 2 times 85 make? 100 and what? $170, right? Okay. And then what's your distance down here? And what's your height here? 95, right? So what's 2 times 95? So a good estimate for a right, or I'm sorry, a left-hand sum distance traveled would be 160 plus 170 plus how much? Okay. What is that? 330 and 190, 520? What would the unit be on this? Okay, so a good left-hand distance would be 520 meters. Now, if I put this down here like this, what's this mean? This part, my friends, right here, definite underestimate. Okay? I gotta go back and read the question on the previous page. But it said, use graphical means to find the distance traveled over that span. Would that be one way to get an estimate? Okay. Well, maybe I'm not left-handed. Maybe I'm what? Maybe I'm right-handed. So guys, can I give you a shortcut to make work a little easier for you on this? You guys never like shortcuts in math, do you?
Never.
I didn't think so. This is not gonna work out this way. I'm gonna move this way. Okay. Set that up front, I think. So let's take a look at some right-hand sums. Okay. I'm gonna draw some right-hand bars over this as best I can. Okay, so a right-hand bar for this one would start at 2 and go all the way up. That'd be a right-hander there. We have a right-hander here. And we have a right-hander. Make these a little darker here in a second. Here. You guys want the shortcut?
Yeah.
Okay. Take a look at this right here. What's the right-hand value up here for this first interval, 0 to 2? So on this red box, we're at the right-hand side for this first one. Isn't that value 85?
Yeah.
Okay, so I'm gonna write down for right hand, I'm gonna write 85 plus, look at your second interval. What's your right hand value here? 95 plus, on the third interval, what's your right hand value clear up here?
110.
Okay, now guys, those are all the heights of each rectangle, aren't they? However, what's the length of all three rectangles? The length's always gonna be the same, so if you can take all the heights of a right hand or a left hand and add them up, oh, this thing is making me mad. Okay, we're gonna take this thing, we're gonna multiply all these heights times what base length did we have for intervals?
2.
2. Okay? Alright? So, we're gonna add 85 and 95, which I think is 180, plus 110, which is, I think, 290. We're gonna take 290 times 2. I've got 580 meters. Okay? Now guys, what do you think I'm gonna put behind 580 meters? Overestimate. My friends, if I wanted to get a really good approximation, knowing that 520 is an underestimate and 580 is an overestimate, what might be one logical thing to do to maybe get a good estimate using left and right hand sums? Average the two. So what we kind of look at here, guys, to figure out a distance traveled is we say, well, let's look at the average of the two. Okay, so a good estimate by right and left hand standards here might be 520 plus 580 divided by what value? 2. What do you get there? Or what's the middle of 520 and 580? 500 and what? So based off of that table, a good estimate for distance traveled in the first 6 seconds, knowing that I time every 2 seconds, a good estimate might be about 550 meters traveled. Okay? That's like going around the track 1.5 times almost in 6 seconds. Is this thing moving pretty fast or not very fast at all?
Way fast.
Way fast. It can almost keep up with me.
Yeah.
Okay. The only thing I can't handle is kryptonite. You missed it. All right. Now, my friends, I want to talk about the effect of changing interval length. Okay, but do you guys have questions on that first example? What did I tell you earlier? If you can multiply and you can add and you know your left from your right, can this make sense?
Yes.
Yes. Okay. Now, guys, example 2 is talking about what happens, what are the effects of changing the interval length? Suppose the velocity of the car was timed every 1 second as opposed to every 2 seconds. What would happen? Okay. This is going to be something that's relative to error. All right. We're really saying the following. Let's make the same exact graph again. Okay. So I'm going to call this 2 seconds down here. I'm going to call this 4. And I'm going to call this 6 right here. Now, I think we had a break in the graph, didn't we?
Yep.
Okay. So my friends, what did I go? 2, 4 up. Okay. So I'll put this little break in the graph down here. And I'm going to call this distance 80. This was where 90 was. This is where 100 meters per second lied. And then well, I got up to 110. Is that right, kids?
Yeah.
Okay, so if I had the points plotted correctly, I think it looked like this. It was 80, 85, 95, and 110, right?
gonna draw my sketch in here. No, I didn't want to do that. Here's what I want. There's my curve, right, kids? Okay, let's pick on that interval from 2 to 4 seconds. Okay, you guys want to work left hand or right hand? Left hand? Okay. So let's draw a left-handed box in here with an interval length of left-hand box, 2 to 4. Okay. So let's just talk about this, kids. Within that box, how long of a time interval are we looking at there? 2 seconds. Okay, and within that one time interval from 2 to 4, is this going to be an estimate that is an overestimate or an underestimate? Okay, I'm going to draw something there quickly. You do the same. Okay, this part right here that I have, right in here, this part right in here, having a tough time with this today, guys. I apologize. Isn't this part right in here the part we haven't accounted for? So if I could figure out that area right there, I could be like, well, you know what? I would know the total distance traveled from 2 to 4 seconds. Okay, this is how far short we are of our estimate. Now the question says, what happens instead of going every 2 seconds, we went every what? Okay, kind of imagine this. Imagine, okay, and we'll draw this in here. Imagine instead of going every 2 seconds, we did left-hand sums every 1 second. Okay, so in other words, instead of going from time 2 to 4, every 1 second would go from time 2 to time what? 2 to time 3. So you would have a box that did this. Okay. Doesn't that box match, first of all, this first half of the gray box here? Okay, but here's the second part of this. If you draw a left-hand sum which goes right to here, fix that quickly. Check it out, kids. What area is left unaccounted for now based on these blue bars? Just this one and this one. So what else got added into for our estimate here? Okay. Now, albeit, is it still an underestimate?
Yeah.
Okay, but what's true about the underestimate? Is it more accurate or is it less accurate? It's going to be more accurate. So the question that we're trying to talk about here is this. It says, suppose the velocity of the car was given every 1 second as opposed to every 2 seconds. What would happen? You would say my estimates would be more accurate. So is it okay to say the shorter the time interval, the more accurate the estimate? Let's write that, okay? So this means the shorter time interval. Okay. The more accurate, or I don't like the way I wrote it. Does it say the shorter the time interval, comma, we get a better estimate or a more accurate estimate? We get a what? Get a more accurate estimate. Okay. So if I start shortening those time intervals, meaning more bars or less bars, guys? Wider bars or thinner bars? Thinner bars are going to be better than wider bars for approximation. That's what this is really saying here, okay?
All right, now guys, here's the deal. All these bars that we've just drawn to get estimates right here, guess what? You don't even have to do that. You can get estimates without even having to put the bars in here. And let me show you how here on this next page, okay? So moving forward here. Are we on this page right here? Is everybody here? Y'all with me on that?
Yep.
Okay. It says finding right and left hand sums without doing what, guys? Okay. You want me to make life very simple for you? Here we go. Take a look at this. This is how I tell kids to do this all the time. I'm giving you another velocity timetable up here again. So if I'm wanting velocity and time on a graph, I would find distance by taking velocity times what? So within each interval, if I know my time interval and I know my velocity height, if I take that velocity times the time interval, that will get you a distance traveled. Well, here's how you do this very easily. First of all, talk to me about your change in time here. In this case, delta t. We're timing every what? So I like to say, okay, we're doing delta t, or change in t is every 2 seconds. Okay? That little triangle just means what's your change in time. Delta t is 2 seconds. All right? Then, this is what I tell kids to do all the time. To get your left-hand sum, simply look at your left-hand values. Your left-hand values are all the values on the left except for the very far right one. Okay? So what are my velocities for left-hand values? 15, 25, and 40. You would simply do, in this table, 2 times 15 plus 25 plus 40. Okay, 15 and 25, what's that add up to? 40 more. What's 2 times 80, kids? A good left-hand estimate from this table without having to graph would be 160 meters. Okay? You guys think this is an overestimate or an underestimate? Why are you thinking under? Because the graph is doing what? Are you speeding up or slowing down? And we'll talk more about that idea right here. Okay? Hey, quick question then. If the left-hand sum said include all the left-hand values except the far right, what do you think it means for right-hand sum then? Do all the right-hand values except for the far left. So I like to circle everything except the far left here. Okay? Sounds kind of political. Far right and far left. Who knew calc could be so political, huh? What's your change in time again, kids? Delta t is a 2. So we're going to go 2 times what 3 right-hand values in this particular case? 25 plus 40 plus what? 60. Okay, I'm not a rocket scientist, but I think that 25, 40, and 60 add to 125. And then 125 times that 2 would get you up. 250. Okay? So my friends, if I've got a right-hand estimate and a left-hand estimate for distance traveled based off of this velocity timetable, how might you come up with an even better estimate knowing what your left and right-hand sums are? Find the average. So we would go 160 plus 250. probably divide that by what?
2.
Okay, so I think my north of Highway 3 math skills tell me that's about 205 meters when you do that. Okay, so based on this table, without even graphing, guys, what might be a good approximation for the distance traveled given those velocities every 2 seconds? 205 meters. Okay, kids, just give me a show of hands. How many are with me to this point right here? Okay, I'm going to go ahead and stop now. We'll pick up the last part tomorrow here.